Water and other liquids are far more efficient than air. You can get anywhere between 50 and 1,000 times more efficient just using liquid. There are some challenges that come along with it, but the overall efficiency is definitely worth it. And in most cases, when you get to the higher densities, it's a necessity. There are really three primary styles or different types of liquid cooling we mainly use. We have liquid to air cooling, rear door heat exchangers. There is direct chip cooling, where you actually inject the fluid directly into a heat exchanger that goes directly on top of the CDUs or GPUs, and that direct targets the heat load. And there's also immersion cooling, which you directly immerse the different components inside a fluid. When you have liquid to air heat exchangers, we mainly talk about rear door heat exchangers. You can have passive or active, and that's the difference between passive and active is if you have fans. But they're basically doors that you can put on the back of your rack. You connect your water to them. They're like radiators, I guess you would say, on the back, and they are easy to manage the airflow directly from the back of the racks, and it removes the heat coming directly from the rack. So you can actually temper the room as well as the incoming air. They're easy to install and operate. They target racks. They make airflow management a lot easier, and you could do it with minimal changes. So there's direct chip cooling, and when we first went into liquid cooling, we kind of weighed the options of rear door heat exchangers, which is liquid to air, and then there's direct chip. Direct chip cooling, we chose that route because you get the water closer to the heat source, and you can target that cooling a little bit better, a little easier. You're not working with as much air. With the rear door heat exchangers, it is more targeted than the traditional hot and cold aisle, and it is a lot more efficient, but you still have a lot of fans and fan noise. With the direct chip cooling, your data center stays cool, and you get that heat noise, or that fan noise is reduced, and it's actually more efficient. And the technology is becoming more apparent that direct chip cooling has a lot more life than the rear door heat exchangers. There's a lot of research out there now where they're getting, cooling at over 1,000 watts per chip. So I see a longer life with the direct chip cooling. They're doing a really good job at heat mapping the hot spots on the chips, and they're targeting those hot spots using 3D printers, specializing their heat exchangers right where the hot spots are, and you could pipe in that water and it comes right out. You don't have any leakage. So there's another style of cooling that's being used in HPC, and that's immersion cooling, where you can use higher facility water temperatures and get a higher return facility water temperature, where they're actually able to maybe reuse those waters and repurpose that heat. But immersion cooling is a type of cooling where you can have this big bathtub type of rack where it's on its side, where it takes up a little bit. It's just a different style of space that it requires, and weight as well. But this big bathtub type rack is filled with this fluid, and the modified hardware that is used, so everything can be actually submersed in this fluid. And they actually use two different types of fluids to do this. And there's still the leaks, the spills. There's a little bit of maybe a mess that people are concerned about, because some of the fluids are an oil-based fluid, but it gives a really good, being immersed in that fluid is a very good thermal environment for the components to dissipate heat. And there's a lot of interest in reusing that heat and repurposing that heat to save energy. To sum it up, you know what's best for your data center. Here at Livermore, we try to stay close with our vendors. We work closely with them. We know what new technologies coming our way. So we try to keep it going in that direction. We try to stay ahead of that curve.